Welcome everybody. This video we are going to continue on chapter 5 and we are going to talk about sketching of root locus. Previously we highlight how the root locus is generated and how the change in the value of the gain will generate different location for the poles of the closed loop transfer function. So as the gain change, the pole of the closed loop transfer function of the control system will be changed and will be moved in a specific path, and this path or the drawing of this path will represent the root locus of our system. So as we said also, there is two main condition actually for the point should be satisfied in order to make it a part of the root locus. The first condition here is according to the characteristic equation. So the characteristic equation for the closed loop transfer function is 1 plus kgs hs equal to 0, because we said for if you have the system here which consists from the open loop or forward transfer function, and there is a backward transfer function which is hs, and usually our gain will be a part of or will be multiplied by the value of the forward transfer function here, or the kgs. So we have kgs, which is the forward, and we have hs, which is the backward. So when we find the closed loop transfer function, it will be kgs over 1 plus kg hs. So usually the denominator of this closed loop transfer function, when we make it equal to 0, we call it the characteristic equation of the control system. So as we can see here, this is the characteristic equation of our control system, which is 1 plus kgs hs. So the k represent the gain of the transfer function, gs represent the forward transfer function, and hs represent the backward transfer function. So the value here, 1 plus kgs hs equal to 0, can give us this when we can represent it by this equation, which is kgs hs equal to -1. So last lecture actually we talked about the two conditions, which is the magnitude condition and the angle condition, and we said any point in the S plane, if we, this is the S plane or our S plane here. So in the S plane here, any point can be a part of the root locus if it is satisfied these two conditions, which is magnitude conditions. So the magnitude condition, that means at this point of S, it should be at this value of K, the condition or the condition should be, or the magnitude should be equal to 1. So for the specific value of K, the specific value of S in real axis, the specific value of S in imaginary axis, when you substitute for this value in this equation, it should give you the magnitude which equal to 1. So the magnitude of the magnitude condition, that means kgs hs equal to 1 for this specific value of k over of gain. And the angle condition here is the angle of kgs hs should be a multiple or an odd multiple of 180. So as we said, if k equal to 0, so it will be 180. If k equal to 1, so it will be 3 times 180, or 3 pi. The first is 1 pi, 3 pi, 5 pi, and so on. So it will be an odd multiple of pi. Okay, so if this point at that specific gain can give you magnitude equal to 1 and angle equal to 1 to pi, or any multiple odd number of pi, so this point represent a part of root locus. So for example, if we have this point here, that point here, so this point must be satisfy the condition of, or these two condition of magnitude and angle. Okay, so if we assume that the kgs hs consists of multiple zeros, which is s plus 01, s plus 02, s plus 03, and so on, and multiple pools, which is s plus p1, s plus p2, s plus p3 in the denominator here. So we can rearrange this equation to get the value of kgs hs, or to make this multiplication of k times the zeros over pools will give you -1. Thus the value of k, or the value of the gain here, will equal to negative summation of S plus Pj over S plus Zi, because actually when we make like cross multiplication for this equation, the pool will go up and the zero will go in the denominator in this equation. So the value of k, which make the point as a part of root locus will be given by this equation, which is S plus Pj for any value or for any pool, and this one for 0. Okay, so we will see now what are the rules that we need to apply or in order to draw our root locus for specific open loop transfer function. So here they are. For sketching the root locus, here we have 8 rules we need to follow. So actually the solution for the question related to the root locus is more structured, and there are rules you need to follow one by one from rule 1 to rule 8 in order to draw the correct and complete root locus of your transfer function. So the first rule here, or rule 1, is more related to the branches. So branches here means how many part of root locus, how many segment of root locus do we have. Okay, so for example, if you have this is the S plane and we have root locus consists of 2 segments, so it should be like this one. One segment should be this one line. Okay, so the number of branches of the root locus, that means the number of the part of your sketch, how many segment or how many part or how many branches, depends on the number of closed loop pools. So you see, if you have 2 pools, so you have 2 branches. If you have 3 pools, you have 3 branches and so on. So the number of root locus segments equal to the number of the infinite pool. Okay, so here we are going to highlight the word finite and infinite, because we are going to see some transfer function they have finite number of pools, finite number of zero, sometimes there is a infinite number of zeros. The second rule here is the symmetry. After you know how many segments do you have, no need to go to draw. Just first to ask yourself about what are the applicability of the second rule, which is symmetry. So if you have 2 root locus, these 2 or 2 segments of root locus, so these 2 segments should be identical around the or symmetry around the real axis. So if you have one segment on the top, you must have one segment at the bottom. If you have have semicircle on the top, you should have semicircle on the bottom. Okay, whatever is the value on the top of the real axis. So actually this is the real axis. This one is the imaginary axis. Real axis means to represent the real number. Imaginary axis to represent the imaginary number. In between them we have the complex number, which is represented by sigma plus minus j omega. Okay, so the symmetry part here, that means your root locus should be symmetry around the real axis. So on the top here should be same. It's like a mirror here. Imagine that that axis is a mirror, so it will reflect what is on the top to become on the bottom the same on both sides of the S plane. The third rule is the real axis segments. So when we said real axis segment, we are only talk or specific our talk on the real axis. Real axis means the x-axis or the sigma axis. We are not talking about the segment which is related to j omega. No, we are talking about this segment on this part, real axis. So here we need to understand how we can know the number of real axis segment of the image, real axis segment of the road locus. So the rule said here on the real axis for k greater than 0, actually always k greater than 0. We do not have gain in negative. Always the gain assumed to be more than 0. We are not talking about the place here. No, the value of k. The value of k not represented in this figure actually. The value of k or the values of k are not showing here. So I can be here and I set k equal to 5. I can be here, I set k equal to 10, I can be here, say k equal to 100, and so on. So the value of k is the value of the gain for the transfer function here. So the root locus exists. That means we have root locus to the left of an odd number of real axes. Odd number of real axes, finite, open loop, pools, or zeros. So in order to understand what we mean by this rule, actually, you can see here the blue segment. Okay, so we have here how many segments? That means blue segment. We have two segments here. Two segments for this transfer function, which is GS. We have GS here. It has two zeros and it has two pools. The zeros here negative Z1 equal to negative 3, Z2 equal to negative 4. The pools P1 is equal to negative 1, P2 is equal to negative 2. So this is the pool. The pool, that means the value which make this equal to 0, which is the denominator of transfer function equal to 0. So here we have, in order to make this denominator equal to 0, so if s equal to negative 1, negative 1 plus 1, so it's 0, so all part will be 0. If s equal to negative 2, so negative 2 plus 2 will be 0, so the whole part of the denominator will be equal to 0. This is for the pool. For the 0, negative 3 plus 3 is 0, so this is the value of the 0 number 1. S equal to negative 4, so it will be 0, so this is the value of the second 0, or 0 number 2. Okay, so if we represent these four values on the S plane, okay, so negative 1, negative 2 representing the pole, so we make them as a cross, as we mentioned before. If you have a pole, you must represent them by cross. If you have a zeros, you must represent them by a circle. Okay, so we have here one circle at negative 3 and another circle at negative 4, so this is another circle. So if we try to apply the rule that we learned now until now, the three rules, the first is number of branches here. Number of branches is equal to the number of poles. That means we have two branch because we have two poles. So we have two branch for or two segment of the root locus. The second here, this should be symmetry around the root locus. If I have a part on the top, I must have on the bottom, but I do not have because my segment here are placed on the real axis. Okay, so in order to know how we can find, do I have a segment here or segment there or segment here or here, how I know that the root locus is placed on the blue segment only or in the area of the blue color here. The rule said on the root locus will be located on the left of an odd number of the poles or zeros. So if I am stopped at negative 1 here, okay, I am on the left. If I am here, if I select any point in this area, is this area on the left of any number of poles or zero here? There is no pole and zero on this area. So all this area there is no root locus. Why? Because I am not on the left of any root in this area. I am not on the left of any zero. I am not on the left of any poles because there is no poles here. There is no zero. So in this area there is no root locus. No root locus. In this area, no root locus. Okay. I come to this area. Am I on the left of an odd number of poles or zero? When we say odd number, I don't mean the negative one. No, I mean how many poles. If I stop here, how many poles and zero on my right? So I'm now on the left, correct? So I'm on the left of how many poles or zero? Now in this area, I am on the left of only one pole. If you are on the left of one pole, or if this segment on the left of one pole or three pole or five poles, so there will be a root locus. So we draw this line. We said yes, in this area there is root locus. Why there is root locus or root locus exists in this area? The root locus exists in this area because this area is on the left of one. It doesn't mean this one. No, I don't mean this one. One means number, a number of one, total number of one of root of pole or zeros. So here I am on the left of only one pole. Okay. Now, if we move to this area here, do I have any, or in this area, I will be on the left of how many poles or how many zeros? Here in this area, I will be on the left of two poles. This is one, this is two, correct? One, two. So I have two poles here. In this area, I am on the left of two poles. If you are on the left of two poles, so two poles means not odd number, it is even number. So there is no root locus exist. Next, if you move to this area, if you stop here, you are on the left of how many poles or how many zeros here? We are in the left of 1, 2, 3. We are on the left of 3 poles and zeros. So this area, we are in the left of odd number of poles and zeros. Since we are on the left of odd number, that means there will be a root locus in this area. Okay, then if we move to this area here, as we said previously, we said all this area no more poles. This area here no poles on zero on the real axis. We do not have any poles and zero, so no root locus in this area. Our root locus will be only in this area and that area. Okay, too. Now, how we can apply this concept to the case of this one? So if you are here, you are on the left of four poles and zero. So this is 1, 2, 3, 4. As I told you, 4 does not mean this number. No, 4 means count. You need to count how many poles and zero on your right, so you are on the left of these poles and zero. Okay, so if you stop here, okay, now we are on the left of 1, 2, 3, 4 poles and zero. So 4 is even number, so we do not have any root locus. We must be on the left of odd number of poles and zeros. I hope it's clear. So this is how to find or how to define the root locus on the real axis. Okay, so as we can see here, we have based on the first rule, since we have two poles, means when we say two poles means count. We count 1, 2. How many poles? 1, 2. We do not say 2 means this 2. No, count 1 pole, 2 poles. If we have 2 poles, so we have 2 root locus branch or segment. Okay, this is the first rule. Second rule, root locus should be symmetry around the real axis. If you have on the top, you must have on the bottom, but in this case we do not have on the top, so we do not have at the bottom. We do not have on the top, we do not have at the bottom of the S plane. Okay, so rule 1 is applicable, rule 2 is not applicable, but we already checked. Okay, then rule 3, the real segment of the root locus should be placed on the left of an odd number of poles on zeros. So we are here on the left of one pole only, one pole. Okay, we are on the left, so there is a root locus here. Here we are on the right, on the left of two poles, not these two poles. This one, number 1, number 2. So we are on the left of two poles, so there is no root locus. We come here, we are on the left of 2 bulls and 1 0. So the total is 3. 3 is odd number here. So there is a root locus. Here we are on the left of 2 bulls and 2 zeros. So the total is 4. 4 is an even number, so there is no root locus here. Okay, so no root locus in this area, no root locus in that area, only we have 2 root locus here. And based on the rule number 1, we must have 2 branches for root locus only. So this is the first branch and this is the second branch. So this represents the root locus for this function according to the 3 rules only. Until now we apply 3 rules. We have more rules. We are going to go one by one. The fourth rule here is about the starting and ending of point for root locus. Okay, if I say the root locus start at this pole, it must be end at that 0. Usually the root locus starts at poles, ends at zeros. So all poles, if you have, for example, usually if you have equal number of poles and zero, for example, I have 2 poles, 2 zeros. So in this case, for example, like the example that we see before, s plus 3 times s plus 4 over s plus 2 times s plus 1. Okay, so here we have 2 bulls, 2 0. We said we have 2 root locus because we have 2 bulls. Each root locus will start at one point and start at one bull and end at 1 0. So as we see here, the root locus usually should start at one bull and end at 1 0. So if we have, for example, if we want to represent this point, for example, here, so I start at the point of -1. If I draw another graph here, so if we have 1 here, this is -1 is a bull. This is negative. Let them. Okay, I want to give another example to explain this. Wait. If we have GS here equal to S plus 1 times S plus 3, for example, over S plus 2 times S plus 4. Okay. So the bulls here, my bulls as will be, if I draw here, bulls will be at -2 and -4, and the zeros will be at -1 and -3. Okay, so this is -3, this is -1. If in order to apply the rule number 4, we said the root locus should start at the pool or finish pool and end at the zeros. So for example, the first root locus should be start from -2, stop at -1. The second root locus should be start from -4, start at -3. Okay, if we apply the second rule also is applicable here because it's actually start from on the left of odd number, so we are on the left of 1 0 here, on the left of odd number, so we are on the left of 2 zeros and 1 bull here. Okay, so this is the representation for root locus. The direction here of the root locus will be from the bull to the zero, so it will be like this one. This is the direction. Always start from the bull point, goes to the 0 point. So the direction of root locus is start from the bull, go to the 0. It's not go, start at the bull, end at 0. Cannot be like this one. Cannot be from 0 to the bull. No, it must be from bull to 0. Okay, So this is the start and end point. So if you do not have finite number, or I mean equal number of pole and zero, that means I may have s plus 2 over s plus 3, s plus 4. So I only have 1 0 and I have 2 poles. So how the poles will be aimed? That means they have to start from -3, end at 1 0, start at -4, and where? I do not have. I have only one pole here, 1 0 here. So where the 0 here? To which place should this pole go to? So should go to. That means we have finite and infinite. So if you have one finite 0 and you have two poles, two finite poles, it means you have also one infinite, sorry, one infinite 0, because number of pole must equal to number of 0. But if you have the transfer function with number of poles greater than number of 0, that means you have the different, or you have the same number of zeros at infinity, okay, in order to make them equal. So number of poles here, or number of 0 must equal to number of poles. But if you have the finite of zeros, for example, is less, that means the rest of 0 will be at infinity, will be located at infinity, okay. So here we can see here number of pole minus number of 0. So if poles and 0 are equals, that means this difference will be 0, no value. But if you have the number of pole is greater than the number of 0, that means there will be a value here. So for example, I have 2 poles, 1 0. That means the difference will be 2 minus 1 will be equal to 1. I have 4 poles, 3 0. So it will be 4 minus 3, it will be equal to 1. I have 5 poles, 1 0. So it will be 5 minus 1, it will be 4 zeros at infinity. Okay. So that means the number of poles and 0 must be equal. If they are not equal, that means we have the rest of the zeros are located in infinity, okay. So if you have zeros located at infinity, we need to apply for rule 4. We need to find we need to apply for root 4 and root 5. If there is no zero at infinity, these points actually will not be important, or this rule are not be more applicable, okay. So we have one point, we call it the centroid point. Centroid point, in order to find the centroid point, at this point we need to draw the direction of the root locus, or the path for root locus to infinity, okay. Since we said we have some zeros are at infinities, zeros are located at infinity if there is a difference in the number of MB and NZ. That means if number of pole not equal to number of finite zeros, that means we have the rest of zeros are located at infinity. So for example, you have four finite poles, one finite zeros. Okay, how this will be in the real case will be like this one. For example, this example, s plus 1, but the poles we have 4, so we have s plus 2, s plus 5 times s plus 6, for example, s plus 7. So for example, here we have 4 poles, we have only 1 0. So number of poles equal to 4, this one is equal to 4, number of 0 equal to 1. So 4 not equal to 1. That means we have 3 infinite zeros at infinity. So if I ask you now, what will be 0 number 1? The first 0, z1 will equal to -1. z2 will equal to infinity. z3 will equal to infinity. z4 will equal to infinity. p1 equal to -2. p2 based on this one equal to -5, b3 equal to -6, b4 equal to -7. Okay, so now each bool here, the bool 1 will start, for example, at -2, will end at -1. Bool 2 will start -5, end in infinity. Bool 3 will start at -6, will end at infinity. Bool 4 will start at -7 and end at infinity. So this is how we can apply this rule. Okay, so you should know how many finite bool do you have, how many finite zero do you have, what is the difference between finite bools and finite zero will be represent the finite the infinite zeros. Okay, so in order to draw the line for between the pools or between the finite pool and the infinite, like this one here, in order to draw this root locus to infinity, we need to have a centroid point and we need to have asymptote. We are going to see in rule 5 which is the asymptote here, or the direction of the poles to infinity. But before we find the asymptote, we need to find the value of centroid point. So the centroid point here is calculated from the summation of real part of poles minus the summation of real part of zeros over number of poles minus number of zeros. What we mean by summation of real part? Because we are talking in the S-plane. S-plane here is real, which is sigma, and imaginary, which is j omega. So when we say the real part of the ball, maybe we have some balls at s equal to 1 plus j3. So what is the real part of this ball? It will be 1. If I have the ball at s equal to 3 plus j5, that means what is the real part of this ball? It will be plus 3. If I have the ball at s equal to -3 plus j5, what is the real part? It will be -3. So when we say the real part of the ball, we means if the ball is located in this area, it's not on the real axis, it's not on the imaginary axis. So the ball will be located in one of the quarter of S plane or S plane here. So that means it will have uh, real part and imaginary part. So in order to find the centroid point, we need to find the real part summation of the ball minus the summation of real part of zero. Then we divide on the number of balls. When we say number of balls, we say here how many balls do we have? We have 4. How many balls? We have 4. How many zero? We have 1 only. Finite. Here we are talking about finite number. We ignore the infinite number. So if I ask you now for this function, how many balls? We have 4 balls. If we want to apply here, it will be 4. How many zeros? Actually, finite zero only 1. The rest all goes to infinity. Okay. So for this function here, we have this transfer function which connect gs equal to k over s times s plus 1, s plus 2. So how many zeros do we have here? At finite zero, zero is no zeros. Number of zeros is equal to, or which is nz equal to 0. No zero here because all the 3 zeros will be located at infinity. All zeros located at infinity. Okay, but how many balls? We have 3 balls. So if we want to substitute here in this equation, so we need to find the real part of the ball. If the balls here are real, so we just put it. So the first ball is 0 plus the second ball is -1, the third ball is -2. So -1 plus 0 is -1 plus -2, it will be -3. Okay, so -1, -2, it will be -3. Okay, -3, and number of ball is 3. Number of 0 is 0. No zeros here. 3 minus 0, it will be 3. So -3 over 3, it will give you -1. So this is the value of centroid, or the point. At this point, we are going to draw the asymptote. Or asymptote is a line which, the root locus will go to the infinity. Okay. So if we move to the rule number 5 here, so the rule number 5 is more on the behavior at infinity. Behavior at infinity, this behavior at infinity come from the asymptote. Asymptote, and we need to find, we already find the value of centroid here. Okay, How to find centroid? We said real part, summation of real part, summation of real pole plus summation of real or real zeros over pole number of poles minus number of zeros. Okay, so according to this equation, sorry, this is negative. Okay, summation of real poles minus summation of real zeros over number of poles minus number of zero, we find the value of or the centroid here. This is the centroid point. Then from this centroid point, we are going to draw the asymptote. So the asymptote here represent a line, and this line goes to infinity, and our root locus will go or in parallel to this line. It will not interact or cross this line. It will go with this line. If this line go there, so our root locus will go there or there. Okay, so this is the asymptote lines. So the number of asymptote actually equal to the number of poles minus number of zeros. So if you have MB minus NZ equal to 3, that means you have 3 asymptotes. If you have MB minus N0 equal to 2, that means you have to asymptote 2 lines or 1 line or 3 lines. It depends on the number of pole minus number of zeros. Okay, the angle of asymptote, as you can see here, this is the if you just remove this, as you can see here from this drawing, you see the asymptote, it has angle with the real axis. This angle, which is phi a1, phi a3, and also phi a2. Okay, so we have 3 angles. Since we have 3 asymptotes, that means we have 3 angles. In order to find the angle here, phi a1, phi a2, and phi a3, we need to apply this formula here. Actually, the angle of asymptote is equal to an odd multiple of 180. So it's the same like the condition that we have before. So it will be 1 plus 2k 180 over number of pole minus number of zeros. So, and the number of pole here in the transfer function is actually depends on how many finite pole do we have, number of zero, also how many finite zero do we have. The value of k here is not the k of the gain. Here is k is a counter, as we mentioned before. K is like a counter, so the value of k will be changed from 0, 1, 2, 3, 4 until we reach to any number. Depends on how many asymptotes do you have. If you have 3 asymptotes, so we are going to take k equal to 0, k equal to 1, k equal to 2. If we have 4 asymptotes, so we are going to take k equal to 0, k equal to 1, k equal to 2, k equal to 3. If we have 2 asymptotes, so k equal to 0, k equal to 1. Okay, so the value of k here will be changed based on the number of asymptotes from 0 to the number the last number of asymptotes. So for example, in this transfer function here, we have 3 poles, we have 0 zeros, no zeros. K here is again, there is no s plus 1 or s plus 2 or any s here. So there is no zeros in this transfer function. We have 3 poles, so number of poles here equal to 3, number of 0 equal to 0. So 3 minus 0, it will give you 3. Okay, the value of k here will be changed since we have 3 poles, so it should be changed for 3 times. I mean, we have 3 poles, that means we have 3 asymptote here. I mean, mb minus nz equal to 3. So we have 3 asymptote, we have 3 value for k, 0, 1, and 2. If we substitute for k equal to 0 here, so it will be 2 times 0, it will be 0. So we have pi over 3. So this is the first angle, which is pi over 3. If I substitute for k equal to 1, so it will be 2 times 1, 2 plus 1, it will be 3. So it will be 3 pi over 3, means 3 pi over 3 equal to pi. Okay, so this is pi 180. If I substitute for k equal to 2, so it will be 2 times 2, it will be 4. 4 plus 1 will be 5. 5 times pi, so we have 5 pi over 3. So this 5 pi over 3 represents like you have 1 pi until this point, 2 pi, again 3 pi, 4 pi, 5 pi over 3. That means it will be negative 60. Okay, so it will be 5 pi over 3 here, will represent the 300. If you use your calculator, it will be 300. 300 means you are starting from this point. This is 180, and 270. When you reach to this area, it's 270. Actually, this is 0. This is 90. This one is 180, and here is 270. So the 300 will be in this area. This is 300. Okay, so if this one is 300 until this point, that means the rest is 60, because the total is 360. So we call it this angle equal to negative 60, either 300 or equivalent to negative 60. Okay, like we said, 270 equivalent to negative 90. Okay, so this is the angle for asymptote. For that, we are going to draw our asymptote at three different angles. The first asymptote with the angle of 60. So as you can see here, the value of the first angle here, this one is 60, or pi over 3. Then the second asymptote will be drawn with angle of 180, and this is the 180 asymptote, because the angle here, when you draw straight line on the real axis, so this angle is 180. Okay, the third will be negative 60, so we count from 0 here by 60, so it will be negative 60. So phi A1 equal to 60, phi A2 equal to 180, phi A3 equal to negative 60. So this how to apply these 5 rules in order to draw the general form of our root locus.